Well, mavens of the microcontroller. Today, we follow our intrepid hero into the land of analog to digital converters. And we're going to hook up an old analog to digital converter. Originally made by National Semiconductor, called an ADC, that's Alpha Delta Charlie 0831. And we're going to hook one of those up. It's an 8-pin DIP, and we're going to hook it up to our vaunted BS2, and we're going to just, and then we're going to hook a potentiometer up to the input going from 0 to 2.5 volts. Now, that being said, what we're dealing with here is converting a real-world, continuously varying value, like the output of a thermistor or a photocell, or measuring some current or voltage or something like that. These signals can take on infinitely many values, and so when we want to bring them into a computer belongs to a class of objects that we call finite state machines. So representing a number whose values are infinitely many in a finite state machine, that is a machine that only has so many states, as you can imagine, just isn't going to happen. So when we measure temperature, say, from a laboratory thermometer or the outdoor thing, we make our best guess at what that value is. We might get a couple of digits of precision out of it, or a couple of digits of accuracy or whatever, but we can't be perfectly accurate, and we have to round off somewhere because we have to write this number down in a notebook or enter it into a digital device or something. At any rate, it can only have a finite number of digits. So a small error is introduced, an error which we are almost always willing to accept if everything is properly designed. Excuse me. So, we have this process of converting a real-world analog signal into a number inside our microcontroller. In this case, we're going to convert it into an 8-bit binary. We're going to convert it into an 8-bit unsigned binary number. So let's just take a look at doing such a thing. So an 8-bit number, let's just review some of the vastly effective binary instruction that you've had. There are 8 bits, and we number these D0, D1, D2, D3, D4, D5, D6, and D7, and we call this one our most significant bit. This is the way our microcontroller works. Other people might represent numbers in a fashion that they like, but a lot of people tend to use this, so some people would call it a big endian format. Goes back to a lot of arguments in the world of microcontrollers, computers actually. All right, so there's your least significant bit. Well, this bit is worth 2 to the 0, which is a 1. This bit is worth 2 to the 1, which is a 2. This bit is worth 2 to the 2, which is a 4. This bit is worth 2 to the 3, which is an 8. This bit is worth 2 to the 4, which is a 16. This bit is worth 2 to the 5, which is a 32. 2 to the 6th, which is 64. And this last bit is 2 to the 7th, or 128. Now, if I have zeros in every digit here, if I had the number 0, 0, 0, 0, 0, 0, 0, 0, base 2, well, that's obviously equal to 0 base 10, okay? And if I had the number 1, 1, 1, 1, 1, 1, 1, 1 base 2, that would be equal to 1 plus 2 plus 4. Well, 4 plus 3 is 7. Add 8, that's 8 plus 7 is 15. 16 and 15 are 31. 32 and 31 are 63. So up to 63. You add 63 and 64, you get 127. You add that to 128, and you get a grand total of 255 base 10. So there's the whole range of unsigned binary numbers that you can get, right? So this represents, by the way, I should have said something here, this represents 0 volts in our analog to digital converter, and this is going to represent, in our hookup, 5 volts. Okay. So, be that as it may, let's you can see all that stuff there. Let's just take a gander at our microcontroller data sheet here. This data sheet covers, you can see a lot of devices. The ADC0831 is a one-channel analog to digital converter, or A to D converter, or ADC. There's a lot of names used. An ADC0832, as you might guess, is a two-channel analog to digital converter. In other words, it could be hooked up to 2 sensors. An ADC0834 has 4 channels, and an ADC0838 has 8 channels. They each convert their inputs to 8 bits, and the I/O connection, instead of presenting 8 bits in parallel using 8 wires, they shift the bits in 1 bit at a time, similar to a serial communication. So they shift the bits in 1 bit at a time, 8 bits, and so it's called 8-bit serial I/O, A to D analog to digital converters with multiplexer options. Now, we don't have any multiplexer options because we're using the simplest one with a single input. And we're going to have a situation very much like this one. See, one side of this potentiometer is at ground, and one side is at 5 volts. And there's the wiper, so I can, out here, I build a voltage divider that can go anywhere from 0 up to 5 volts, and then I can put that into an analog to digital controller. In our case, I'm going to put it into an ADC0831, and there's a signal here called chip select, and so it kind of enables the chip. And if you see the bar over it, that's a Boolean algebra notation. It means this signal is active when it is low. All right. Of course, we have ground and power, 5 volts here. We also have a signal called a clock. That's how we're going to tell the device to give us each bit on this DO, or data out pin. VREF sets the maximum value for the analog to digital conversion, and so VREF is connected to VCC because we're going to 5 volts. VCC is 5 volts and this thing ground is 0. VIN, this is actually a differential input converter. We're going to use it as a single-ended input converter, so we're going to connect our input to pin 2 here, VIN plus, and we're just going to connect VIN minus to ground. So we're always looking at the difference between our signal and ground, which is another way of saying we're looking at our signal. So our potentiometer, the wiper will come into pin 2 here, and pin 3 will be connected to ground. So that's our hookup. I'm going to go over to the Windows side here. Here we go. And now I've gone out of my way to make a very confusing diagram here. This is the PBasic editor, and so I created a program ADC0831 under 0001.bs2, and really the program is, I just stole the parallax program for, talking to an ADC0831. This chip's been around for a long time. I've actually used these. I'm thinking 80s, maybe into the 90s. I don't know, but I think, maybe into the 90s. So the chip's probably been around 30 years, or at least 25 years, or something like that. It's still sold, so it must be an effective chip, low cost, does a good job. Now, lots of digital systems, as you may or may not know, I hope you do, are driven by a clock signal. It's a periodic rectangular waveform where the rising edges and or falling edges denote timing events and allow systems to operate sequentially. So they go from state to state to state, and the state transitions happen either on the rising or falling edge of the clock. In the ADC0831, the falling edge of the clock, causes a change in the DAT output. So you can see the CSL here, the chip select low. That starts out high, but you have to drive it low to kind of enable the. Some people would call these chip enables instead of chip selects, but so you enable the chip by driving this low, and the first clock pulse after CS is low. The falling edge will cause the data to go. See how I have the data drawn here kind of at a mid-level? So the top of these would be 5 volts and the bottom would be 0 volts. This whole thing is called a timing diagram for obvious reasons. Time progresses to the right, kind of like it would on an oscilloscope or a logic analyzer or that sort of thing. And what happens here is this first bit is a 0 and doesn't give us any information, but the output goes from what they call a high impedance or an undriven state, usually represented as mid-supply or somewhere in there. It probably is more like, floating up near the supply voltage, but this indicates that it's just not driven and you can't take any data there. So after the falling edge of the first clock, after chip select low has been driven low, the first data bit is a 0. And it's really just before the rising edge of the clock is where they sample for stable data. I put rising edge of clock as a good place to sample stable data, but it's really just before it, and it's really timed off of this falling edge, but just put it there. So the first data bit is ignored. Then we have our most significant bit, D7, D6, and then it gets less significant as you're on D5, D4, D3, D2, D0, D1, D0, and the timing diagram goes on like that. And this is, I grabbed this from the data sheet, but this is actually not how Parallax chooses to do it. They do it correctly. Their stuff works. So they tend to have 1, 2, 3, 4, 5, 6, 7, 8, 9 bits. And they sample this last bit just as a timing off of here, internal to the microcontroller. So these last 3 clock pulses don't even happen with Parallax. And say, well, how do you get the last data bit here? Remember, we're not actually using this rising edge. We're timing off this falling edge to a time that's just before the rising edge. And so the microcontroller seems to do that. And that's all part of a special instruction in the Parallax P-basic language called shift in. And what it probably should have done is, instead of using shift in, I probably should have written a for loop that actually banged out the clock bits manually so you could see it that way. But we will take a look at the oscilloscope and see what we have on there. So here again, here's our hookup. The 5 volts goes to pin 8 and the ground goes to pin 4. In minus is grounded, so even though this is a differential input, we use it in a single-ended form. The pot wiper goes to in plus. Now from the BS2, P0 becomes our CSL line. P1 becomes our clock line. So these are both driven from the basic stamp. And then this data line is driven from the analog to digital converter back to the BS2. So, maybe what I really should do is kind of put some arrow data in here. So that is an output from that guy, and this one goes that way. And let's see. Yeah, something like that I think is the right way to do that. So these arrows indicate that the BS2 is driving the chip select low signal, or chip select active low signal, and the clock signal, and the DAT, or data line, is being driven back from the analog to digital controller back to the BS2. Okay, so after all that, our program is rather simple. We give names to the clock pins. That's good thing to do. And we have a byte variable called ADC result. So the first thing we do is we take the chip select high and we deselect the ADC 0831. Then in the loop below, you can read this thing. Because the ADC 0831 wastes that first bit, this is going to be a 9-bit transfer, so there's 9 clocks in there, 9 clock pulses, which you'll see on the scope. So what do you do in this main program? You drive the chip select low. That activates the ADC 0831. Then you perform this shift in instruction using the DAT line for data coming back, the clock line to drive a clock. MSB post is just some parallaxes for the fact that they want to sample the data somewhere after the falling clock edge and before the rising edge, and the MSB is the first bit. So instead of D0, D1, D2, it's D7 is first, MSB is first. So that's wonderful. So what we're going to do is the shift in instruction. We're going to put the result in ADC under result. The \9 means that there's 9 bits to shift in. MSB post again says where the data is and whether it's most significant bit first or least significant bit first. Once we get that data in, we take the chip select active low signal, we take it back high to deactivate or deselect the ADC 0831, and then we print out the conversion result, and we're going to print it out in decimal. And I think maybe we should print it out both in decimal and binary. So I forgot what the question mark was. I thought that's where you type something in, but I guess not. So, well, let's take a look at the program first of all and see what we've got. And let me bring this mess over here. And I'm going to go back. Now you can see I'm getting a result of 129. I'm going to try to make that 128. It's a pretty touchy adjustment to do that. There, it's 128. If I clear it, you see that each second I'm getting 128. Now let's go back over to here, and you can see that my value is very close to 2.5 volts, 2.494 volts. And that's half of 5 volts, just like 128 is half of 255. Well, 256, but 255 is our highest number. So you can see that we have half of our maximum number, and we're looking at half of our maximum voltage. Now what I'm going to do, I'm going to try my usual schlocky way of showing you the scope trace. The scope is on both the clock and the data, and I could show you the chip select, but all it is, it just goes low while we're looking at things. Now let's see what we've got here. Come on. So if you look at that, right now I have 1, 2, 3, 4, 5, 6, 7, 8, 9 bits. Okay, and it appears to me that this first bit is garbage. We have a 0 there. Then we have a 1. Okay, so that's 128. And then I've got 1, 2, 3, 4, 5, 6 zeros and a 1. So if we go back, I think we're going to be looking at let's see, is it saying 128? Oh, let me here, let's do this. So it looks like 128. There we go. Now you can see the scope. It only has the bit for 128. D7 is high. So if I take it to another place, let's take it to another voltage. Let's say 3 volts. So I'll bring it back here. And sorry about all that. I just don't have the fancy camera set up. But let's set this. I'm going to go in here with a screwdriver and change the potentiometer. Oops, that's a little tough to see the voltage. There's 3. Okay, let's make it. How about 3.4? Whoop. 3.5. No. 3.3. Better yet. 3.3 volts, 3.29. Okay, so if we go over here, we got a new number now. We're getting 170. So what if I were to change this program and say I want bin ADC result here, and maybe I'll put some kind of character like a colon in between so we don't have any trouble there. And we'll try programming that. And it's giving us a carriage return. I don't know why. I wonder what this... Let's just get rid of the question mark. Do we really need that thing? Well, apparently we do. Here, we'll go deck. And we'll put our own carriage return after this. Here we go. Now we're getting 170, and I'm getting, oh, look at this. I picked a good number. I'm getting 10101010. Okay. So let's come back over here and let's look at 10101010. By the way, oh, you want to see what that looks like on the scope? Probably that would be a lot of interesting data bits. So let's take this thing over here and look at the scope, and I got my old display is on there right now. Just give me a second and I will rectify that. I won't change it from AC to DC. Oh, boom, there we go. Right after the first bit, that 0 is garbage. Okay? So that 0 is garbage, we ignore it. Then I got a 1 0, 1 0. 1 0 1 and then 0, because the sampling happens sometime after that last bit. So 1 0 1 0 1 0 1 0 in binary. All right. And just let Mr. Wizard move these things around here. Okay, yeah, this light gets a bit bright. So let's do a little math here. So we have, if we have 1 0 1 0 1 0 1 0, that means we've got 128, right? We don't have 64, but we do have 32. We don't have 16, but we do have 8. We don't have 4, but we do have 2. So, let's see if I can do this in my head and screw it up. Well, 32 and 8 is 40. And 2 and 128 is 130. So you get 170, and that's what we saw print out. Okay? So now let's make a proportion. We got 170 is, and you'd think I'd use 255, but the right thing to do here, since we go from 0 to 255, is to use 256. So 170 is to 256 as some voltage V is to 5 volts, right? Okay. So now you could cross multiply here and get 5 times 170 equals 256 V, and this guy would be 500 plus 350, so this will be 850 is equal to 256 V, and V will be equal to 850 divided by 256. Survey says, let's bring down the Billy Barul here, light him up. Okay, and we've got 850 divided by 256, and I get 3.32 essentially. So that's equal to 3.32 volts, and we were reading like 3.30 or 3.29. So, hey, not too shabby, eh? Eh? All right. So, that's basically what we do with this thing. I'll do one more example here, and then we'll declare victory on this analog to digital converter deal. Let's see. We can try a small number. How about something? Wait a minute, I'm off on the wrong axis here. So let's try something below 2.5. Let's try something around, I think, 1. It might, I don't know. I was going to try something like 1.666. Oh, no. Oh, screw it. 1 point. There we go. 1 point. Let's call it 1.75. Okay. Let's go over to our place over here. I'm going to clear it, and we are seeing 91 in decimal. And we're seeing 1011. We're only seeing 7 digits. So we have to make this a little better. We have to have this say bin 8. And when we do that, and run it, it forces it to put in the leading zeros. So now we have 0101 1011, and let's see. Okay, so let's see what we got here. I don't know if we'll get any sharper, but yeah, not too bad. All right. Remember, the first bit, this first 0 is thrown away. So after this clock pulse right here, we have a 0. Then we have a 1. So I got 0, 1, 0. Whoops, sorry. 1, 1, 0, 1, 1. That's what it looks like to me. So I got 0, 1, 0, 1. Then 1, 0, 1, 1. Okay. All right. So let's run the calculation on that and see how we do. Now, probably should write this one down. So this time we've got hold on. This time we've got 0, 1, 0, 1, and we've got 1, 0, 1, 1. Okay. So that tells me I've got a 1, a 2, no 4s, I've got an 8, I've got a 16, no 32s, and I've got a 64. Alright. Well, 64 and 16 gets me, so that gets me to 80, 88. And 3 more is 91. So the 91 was right. So let's do our proportion here. 91 is to 256 equals V is to 5. So 5 times 91 is 455. Because 5 times 9 is 45, but it's 90, so it's 450. 5 times 1 is 5, 455 equals 256 V. So V is 4, 5, 5 divided by 2, 5, 6 equals 455 divided by 256. Boom, 1777. So this is 1.777 volts. My meter is still saying 1.751. What would happen to these two cases if I use 255? I think some people say you should use the 255. Well, let's just take a gander. Maybe it makes it come out better. So up here I would have had 170 over 255, sorry, equals V over 5, and I would have had my 850 over 255 equals V, and that would have given me what? That would have given me an even higher voltage. It was a 3.33 instead of 3.32. So that's not going to help us. It's going to make this voltage even higher. So that's as close as we get, though. So anyway, there you go. We just measured a couple voltages. It looks to me like within 1%. All right. So we just measured with an 8-bit A to D converter. We just measured 2 voltages within 1%, which is not too shabby. And we converted some continuous time signal coming off a potentiometer, which could have been a thermistor, could have been any, could have been a pressure sensor of some kind, could have been any kind of sensor. It could have been a 4 to 20 milliamp current loop where when you convert it to a voltage, you bring it to the analog to digital converter. You do the magic interfacing by reading the data sheet and all that kind of stuff. And, by going through all that, you see, in this case, bits were communicated serially, one after another, using only 3 wires instead of, with 8-bit, you would need to read at least 8 wires, and you'd probably need like a 9th wire to say data is valid kind of thing, So you saved a bunch of pins, which are always worth money in a microcontroller project, and you made a voltage measurement. So in this case, we just made a voltmeter, all right, 0 to 5 volt voltmeter. But that's a lot of times that's what reading sensors are. It could be voltage or current or whatever. But the sensor is turning some real-world quantity into a voltage, and we're measuring it. So at that point, we'll say adieu, and we'll probably have some homework, messing around with some of this binary decimal, read a sensor and get a voltage kind of thing. So until next time, be safe, take it easy, tip your waiters and waitresses. They work hard for the money, and we'll see you soon. All right, bye-bye.